Hello everyone, my name is Dmitrii Smirnov. I am a software architect at AOSTO software development company. I am glad to introduce my presentation about development of software-defined storage engine for 25 million IOPS. Let's start with the agenda. Today I will tell you about modern hardware technologies, some important milestones, today's problems and challenges. Then I will talk about existing software-defined solutions, their performance and capabilities. After some investigations, I will tell you about an interesting storage project in the Linux kernel and SPDK. We'll describe development process step by step with its challenges, mistakes and results. So let's start. Modern CPU and NVMe technologies have made a breakthrough and have opened new horizons for software-defined storage performance. AMD with 64 CPU cores and PCI Express 4, NVMe SSDs with over 1 million IOPS on random read and over 6 GB per second on sequential read, network adapters with 200 and 400 GB per second, and new JBoss. Theoretically, single-node storage platform would provide over 24 million IOPS or 100 GB per second. But if we look at the market, we see solutions with 6 or 10 million IOPS per node performance, even if they use modern AMD and 24 NVMe SSDs. Customers who require tens of million IOPS for their HPC, AI, machine learning use cases are forced to buy more servers to achieve necessary performance. I believe that not everyone is aware of the new software storage performance or considers it unreachable. I believe that current software solutions are not ready for new hardware capabilities. I believe that today we can create more efficient storage systems. We should push software limits and be prepared for the new performance opportunities. So the challenge. Let's get the best performance from existing software on modern AMD, CPU and internal NVMe SSDs. At first, let's find or develop a software-defined storage engine for a platform with 24 million IOPS on a random read. And don't forget about the future hardware and future markets. We need SDS to build the future disaggregated storage. Today, we will test block storage on a single node platform. In the future, we should build a composable storage, so our local tests should reveal the full potential performance. Existing open source solutions, Linux MD RAID, Linux Volume Manager, SPDK RAID, and SPDK Volume Manager. Of course, kernel and SPDK-based software solutions have their limitations, but we should know about their performance. We made some tests, and you could see the results. Our platform provides 25 million IOPS, which is poor NVMe performance. Nice to know that SPDK can provide maximum NVMe performance. LVM, actually striping without erasure coding, also has the maximum performance. But we need data consistency and fault tolerance, and unfortunately, MD RAID has terrible IOPS and latency. Let's make a research. Before we start, I have a few questions to answer. Why I am only testing read-intensive workload? The reason for this test is to identify software bottlenecks. Each complex benchmark consists of a simple workloads, so I need to know the performance results of simple synthetic data-intensive read workload. What about SPDK RAID and volume? Of course, we can use SPDK RAID 5, ISAL erasure coding, data services like theme provisioning and snapshots. But as of today, SPDK has limitations, and we need a solution for the future multi-node active storage cluster. So what about the kernel? It seems that the kernel stack is not CPU friendly. because CPU is the most important resource for our performance. There is an excellent book by Paul McKinney about software performance, and today I will try to combine the ideas from the book with software-defined storage solutions, data paths, and data sources. Our main approach is testing on null or RAM virtual devices because it shows real performance bottlenecks well. We made some tests with RAM virtual devices and a kernel block stack without SPDK because SPDK has no performance issues. Our platform provides 50 million IOPS, which is the possible kernel performance. LVM has no problems. It confirms that LVM can provide 25 million IOPS on NVMe. But MD-RAID has huge bottlenecks somewhere, even MD-RAID 0 without any complex logic. So the result is that we have to develop a software-defined storage engine for our future projects. At first, the requirements for our MVP will be simple, without snapshots, clones, deduplication. But we should design the necessary features, the entire data path, array decoding, theme provisioning, metadata, rebuild, and recovery services. We need a unified engine for both kernel and SPDK with the same logic, algorithms, but slight API differences for easy maintenance. Also, the must-have feature kernel block device and SPDK virtual BDF, and as much performance as possible. A unified SDS engine should be suitable for all use cases and get all benefits of each environment. SPDK has many performance benefits, but the SPDK architecture requires a lockless design, event-driven and polling-based data services. On the other hand, Linux kernel has less design requirements, and you can build and use block device as it is. Don't forget that we need the same code base, so let's start with kernel development and hope we get the full performance. As you can see in the storage model, our SDS is called STO, just STO. And it fits into storage sources in both SPDK and kernel as a simple block device abstraction. At first, we developed the first version of our SDS and tested it with NVMe. But what a surprise, we have terrible IOPS, less than 20 million. The latency is okay. Anyway, this SDS has bottlenecks, let's research. And let's start from RAM and bottleneck testing. Of course, we have bottlenecks. Only 23 million IOPS on RAM, but we need over 35 million on RAM. Where are the bottlenecks? That is the question. How can we find bottlenecks in kernel software or in software-defined storage? By disabling components step by step. Probably bottlenecks are not only in our software, but also in the kernel block stack or in a kernel API. Don't forget, the CPU is the main resource. And we found problems. Firstly, the kernel block multi-queue is the first problem, because currently it's not designed to provide full kernel performance. Also, the device mapper and existing block schedulers, deadline and BFQ, are also not high-performance solutions. So we need to exclude them from our stack. The next problem is kernel thread management, queue work and car-thread queue work. Every moving from current contacts, even within the same CPU, could waste millions of IOPS. Next, memory. Actually, Cache is what I like, because per CPU memory allocator is a great thing. But even Cache could waste millions of IOPS if you use it too often. Spin locks are evil, well known, but fine-grained object design and RCU sometimes are okay. Unfortunately, these methods are not a good solution for write mostly objects and multi-million IOPS workload. So what about our solutions? Firstly, for the kernel block device, you should use a BIOS-based queue and develop your own I/O merging. Next, forget about queue works and moving between car threads. Try to design a fully per CPU architecture, optionally with your own local SKUs. In the book about software performance, you can find great techniques about parallel programming and wave-free algorithms. So it should be enough to build a per CPU database. In Linux kernel, you can find local lists and per CPU libraries. I want to share some ideas for building lockless data sources. The huge problem in storage is the multi-tenancy problem. It's all about noisy neighbors. The idea of parallel data source design is to make everything per CPU or per thread. For quality of service features, we can use simple lockless ring buffers for per CPU data. For the volume manager and its mapping tables, we have to use per CPU reserved areas, so different I/O sequences will be mapped in parallel. Without block schedulers, we can use per CPU trees to build I/O sequences and merge I/O. Instead of a global cache, we can use a per thread stripe cache, and not forget about the LRU policy. The big challenge is building a parallel journal, snapshots and clones, using copy on write and redirect on write algorithms. In this case, it's hard to integrate a per CPU design, so we can use fine-grained bitmaps instead of spin logs for data consistency, and reserved areas for different I/O sequences when redirecting new data. After integrating these localist design ideas into our kernel SDS, we integrated them into our SPDK SDS and got a fully per-thread architecture. So here are the results from our second version of SDS. Firstly, on a RAM environment. 36 million IOPS on RAM. It should be enough. Let's return to real NVMe testing. Thanks to per CPU design and bottleneck research, we have achieved 25 million IOPS from NVMe devices. It was hard in kernel, but it is a necessary design for the SPDK storage. Let's summarize kernel and SPDK development. In kernel, you have a lot of tools to build software-defined block storage, even without high performance. It has no complex design requirements, so you can design what you want. But you have to spend all your time exploring the kernel bottlenecks. On the other hand, SPDK guarantees you the highest performance, but you should spend all your time designing lockless data sources. The silver bullet is to design a lockless architecture from scratch and use it in both kernel and SPDK. And read a great book about software performance. A few slides about common mistakes. We removed this potential bottleneck and didn't notice an increase in performance. Probably not a problem. Actually, it's a problem. Mostly a huge bottleneck hides a smaller bottleneck. So after you fix a huge problem, you will find that even IO request counter costs millions of IOPS. Let's optimize data path, but the background data source will not. It's a bad idea, because performance optimization approach, all or nothing. You should optimize both data path and data sources. The more efficiently a background data source uses CPU, the more resources remain for the data path, and the more IOPS you get. Let's not reinvent the wheel, use the generic system API and hope it's optimized. Don't be sure other developers are testing on the highest performance hardware and they have the same IOPS requirements. A few words about this performance and benchmarks. The idea of presentation was to show you an approach to bottleneck research. A simple synthetic read-intensive workload helped us build a software without huge bottlenecks. It can also help us get a high performance on real workloads. Modern hardware needs modern software. so we always need to optimize our stack, no matter it's a single node storage or a disaggregated cluster. What's next? I hope this presentation will help you build your software-defined data center. And we will continue to develop high-performance storage solutions and share our knowledge about disaggregated storage, kernel, and SPDK optimizations with you. Thank you.